barrel, and that's what's going to allow the projectile to actually be fired, taking an input from the control system.
Right here we have a block diagram of the electrical control system, the heart of that, of course, being the Raspberry Pi 3, and that is the red block. To the left, we have the two sensory inputs, one measuring the angular displacement of the barrel, the other one the pressure in the chamber. To the right, we have the actuating signals for the solenoid valves, depending on whether you are filling the chamber or launching. At the bottom, that shows the touchscreen interface, which, as we mentioned, is the interface of the control system. The bottom right shows a schematic of the power supply unit, which we're going to get into right now. To regulate the 12 volts that we're using from the battery down to a constant 5 volt signal, we needed to use the LM338 chip right here. This has a high current output, so it should be able to handle any load that we place on it. There's no current simulation models of this chip that are readily available, so we wrote one using SPICE software, and we wanted to simulate the circuit to make sure that it would at least perform relatively close to as expected in real life. So right here, this represents the output of the simulation. We compared the output of that regulator against two input parameters, the battery voltage and the output current. We need to know how it performs against the diminishing battery voltage as the system is operated over the day, and we also need to know how it performs as different loads are placed on it. So whether the Pi is performing calculations or holding one of the valves open, we need to know that at all points it's going to meet at least the minimum required voltage for the Pi, which is represented by the black plane. That's 4.75 volts. This is the schematic for the power supply unit and additional circuitry. To the right, we have the 12 volts to the 5 volts, the regulator with the LM338 chip. In the middle, we have a filter and a buffer for the analog signal coming from the pressure transducer. That way it's received in its full integrity at the analog to digital converter, which converts it to a form that the Pi is able to interpret easily. This right here is the actuating circuit for the solenoid valves. When the GPIO pin goes high, current is allowed to flow to the valve, either filling the cylinder or launching the projectile. When the GPIO pin is at 0 volts, no current can flow to the solenoid valve, holding it closed because it's normally closed and cutting off that component that it controls from the rest of the system.
So here's a list of NSPE, IEEE, and ASME codes of ethics that apply to our project, with the most fundamental code being the first fundamental code regarding safety, health, and welfare of the public.
In keeping with our first fundamental code of NSPE, our main concern with this project was safety. Our main risk, obviously, is high pressure, and so our main point of concern was the pressure cylinder. To alleviate that concern, what we've done is installed a 175 manual/automatic pressure release valve. If the pressure cylinder ever reaches a point that is over 175 psi, that valve will automatically open, releasing the pressure. There is also a manual option. If the user ever desires to relieve the pressure themselves, all they need to do is pull that ring on the top. We also have a no launch feature that's based on an angle sensory input to the control system. So if the barrel ever drops to a point that is beneath 15 degrees above the horizontal, that will lock out the system. That ensures that everyone in the vicinity of the device is safe and that it is not used improperly. We have our computer actuated solenoid valves for both pressurizing the cylinder and firing the projectile. That ensures that the pressure cylinder never reaches a point of overpressure, and also that the user can be away from the assembly while it is firing. We have high safety factors for all of our pressurized components, as well as structural. And in the future, we aim to write safety guidelines and a full user manual for the project.
To confirm the safety, we conducted multiple simulations on the major load-bearing components, including the pressure cylinder, leg, barrel, and barrel hinge. Each of the applied forces were exaggerated well above our expected working forces to accommodate for any SolidWorks errors, errors in the simulation. So for example, the single leg close has an applied force of 60 pounds. That is the estimate of what our design is going to weigh. In reality, that 60-pound force is going to be distributed across 2 legs, not 1. And even with this exaggerated force, you can see that the safety factors are well above recommended. So our current future progress, we have completed all of our calculations and finalized our mechanical and electrical designs. We have checked the inventory of Wilkes University and collected any materials that we need. And we've determined a testing location and method for our prototype. Next semester, we will be finalizing our design, our drawing package, and our projectile mold design. We will also be fabricating our product and putting it through extensive testing. And lastly, we will be creating a user guide, safety manual, and troubleshooting guide similar to one you would see in a commercial product. Lastly, we would like to note that we worked an average of about 16 hours a week individually on this project for the entirety of the semester. We would also Lastly, we would like to thank our advisors, Dr. Damari, Dr. Anaya, and Professor Taylor, for their assistance and support in the completion of this project.
We would also like to thank all of the EE and ME faculty who taught the courses that we had in the past 3 years, giving us the knowledge that we applied to the design of this project.
We would also like to give a special thanks to Mr. Mitch Adams for offering all of his expertise and help with the fabrication portion of this project.
So, with everything we've talked about in mind, does anybody have any questions regarding the Overcast? Yes.
What regulatory body are you, whose regulations are you following for your pressure vessel?
We're following the NSPE, IEEE, and ASME standards for that. And for the safety
Only
as
one
well.
of those regulates pressure vessels.
Specifically the pressure vessel, that would likely be ASME.
Likely?
Yep. Well, that's something that we'll have to look into more specifically.
I guarantee you it's ASME. For a product like this, a commercial product, you must go through ASME for pressure vessel codes.
Okay.
Now, is this always going to be filled with 125 psi, and then you're just going to modulate how long the solenoid is open?
No. So, as it stands, what will happen is after the user inputs a distance, then the control system is going to calculate how much pressure is needed, and then from your pressure source, whether it's a tank or the air compressor, the solenoid valve is going to be kept open long enough until it reaches that point of pressure, the required pressure, and then it's going to close the solenoid valve. You only have as much
It's going
pressure.
to automatically tell the...
Yes.
Okay.
Yes.
My next question is, what if I'm playing Frisbee and not paying attention and I run it 10 feet in front of this thing, right as it fires? What's going to happen to me?
Yeah, so we plan to have a safety message displayed on the LCD warning the user that before they launch, they have to make sure that everything is clear in front of it, so no people, even people running around on the sides, no objects in the way. So that's going to be largely dependent on the user. The whole goal of the safety documentation is to provide them with enough knowledge to know when exactly they should be operating and how.
We also included a safety feature making it so that it will not launch if it's below a certain angle.
Sure.
The barrel is 4 feet long, so the exit of the barrel is going to be about 4.5 to 5 feet off the ground.
And
What muzzle velocity do you anticipate?
We're anticipating anywhere for the max 300 yards, our calculation is a little over 200 feet.
20 feet per second for... That could kill someone. Okay? You need to look up local laws and regulations for states. For example, Wyoming, they're not going to care. If I bring this into a beach in New Jersey, I'm going to get arrested. Okay? Now, an engineering question. This is muzzle loading, right?
yes.
Okay, so you have the filament coming out the back of this. It's going to be rubbing up. It's going to be compressed between the wall
We have a
of that,
tolerance gap of about 1/16 of an inch.
a 16th of an inch. You're going to have a lot of vibration there. That's the reason the musket balls have terrible accuracy, is they have very poor tolerances. What kind of accuracy do you anticipate with this? Or is that not a concern?
So the accuracy is not a concern down to like, say, the nearest couple of yards. We're going to try to get it within a range of about 10 to 20 yards from the user input distance.
To address this issue, we're also looking at using projectile and vegetable oil to make a seal around the for aeration around the
Okay. My concern, though, is just as this exits the barrel, there's going to be wear on your fishing line.
Yes.
That it's just going to come out and just need to snap. Or it's going to come out and already work through.
We've already thought about that. We purchased a 100-pound test monofilament shock leader that is designed, it's going to be very flexible and designed to absorb the initial shock, and it's also very abrasion resistant.
Yeah, as for the abrasion as it's coming out of the barrel, as you mentioned, we have that 16th of an inch, but as you put the projectile in, it's already going to melt it a little bit around the outside, so you will have some fluid there to kind of keep that.
Okay.
Dr. Henry?
My concern is on the software end of it. You've got a lot of things that you need to cover.
Yes.
Besides the safety stuff and the operational stuff and so on, there's a lot there. Have you clearly defined all of your software requirements? And do you have are you going to be developing an acceptance test plan for this to make sure that you satisfy all of those?
Yeah, so right here is actually a block diagram of the software flow right here. So we have the idea
say, I'm testing this specific thing, which is, the pressure thing was an ideal one when you talked about, it's going to, you can tell it the weight, all of this other stuff that you put in, and it's going to define that, what pressure it's going to set the thing to. That's a requirement.
Yeah.
You're going to test it.
Yes.
Okay? So there's a lot more to it than that.
Yes, we do have testing plans for all of our components. So we're going to test them individually before integrating them as a whole system.
How's the user going to know the angle that things are set at? Is it built into the display that you're going to have?
Yes, there's going to be a readout on the screen. So it's going to automatically change as the user moves the barrel up and down the direction of the system.
And so you're able to read the angle when they put it up to 15 degrees or 25 or 45 degrees. What's
Yeah,
the maximum angle you're going to be able to set it at then?
So right now, we're assuming our ideal launch angle is 45 degrees because that's what we have to go with right now. We'll correct that as we have a better idea of how our system performs in real life. But we have a 25-degree range of motion, and most beaches aren't going to slope down to below 10, 15 degrees.
Yeah.
So we have enough to compensate for that.
And remember, your target isn't a bullseye. Your target is distance.
Exactly.
So with Dave's question, it was, accuracy is distance is what you're measuring. So that's your goal is distance. So remember that. Thank you.
Thank you very much. I was gonna say they're the snazziest dressed team.
That's very nice.
They're pinned, yeah, they're pinned as their logo.
Guys,
That's pretty nice.
love the uniform.
I was like they're all dressed